two great papers that I didn't give you copies of because they are very detailed and very specific to the topic that we are touching on right now. The first one is a very good PowerPoint presentation that was prepared by two wonderful colleagues of mine. That's Thorsten Möller and Han-Wei Shen. So Han-Wei Shen is at the Ohio State University, and Thorsten Möller is at Simon Fraser University in Vancouver. They are both leaders in this field of visualization. And many of you have already read papers of them. Okay, I'm pretty sure. And so they have a very good PowerPoint presentation that's an overview of all of the essentials of flow visualization. They also talk about these things that I talked about last time: streamlines, streak lines, path lines, and the difference between them. Okay, and they also explain it much better in the PowerPoint than I had time for last time. The other thing is this great paper, a more theoretical paper, a mathematical paper by Greg Nielsen and his student at the time. It's about computing tangent curves. It's another word for computing stream curves. Okay, and in fact he goes into the actual exact solutions of certain types of differential equations when you can actually compute these tangent curves exactly, analytically, not numerically. Okay, and so when you look at these two papers, they might give you ideas for your final project. If you were to focus on vector fields, flow fields, okay, there's lots of materials in there that should stimulate you. And again, they are both freely available. This is a transactions paper, Transactions on Visualization on Computer Graphics, and the UC Davis has a subscription to it, so you can get to it. All right. The other interesting thing for all of us, of course, is to look at the demos. And the first project is due a week from today, so you can ask me the last questions, right, tonight. Think about your questions. The other thing is I would suggest that we just begin the demos in this room about 7:40, and then we go for as many projects as are ready to be looked at on that night. Okay? Some of you will sign up tonight, but will still want to prolong it and then do it on Thursday night. Okay. No. So anyway, sign-up sheet is here. Yeah, one second, Misha. So there are 24 students in class. So I hope to have maybe about 12 demos, 1 hour, Tuesday night, and maybe 12 demos the following Thursday night. Okay. I realize that maybe 1 or 2 or 3 of you will need additional time. It's fine. It will work against you, right? I mean, so try to do it next Tuesday. If not next Tuesday, then Thursday. Sign-up sheet. So who will demo? Who intends to demo on Tuesday? Basically, I just need to count. I need to count the number. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's about half. Okay, that's good. So assume that we will use up about an hour. Okay, from 7:40 to 8:40, and then there is the issue of: do you like your fellow student to look over your shoulders when you are demonstrating your project to me? Kind of like an open demo. Right? Some students like it, some students don't like that. It's really between the student and me, right? And so there are some issues being discussed. That was great. This didn't quite work. So it's kind of like a private thing. If some of you object to making this open, then I will be happy to do that kind of like more privately, and only it's a student and me, and then people show up whenever their time slot is. Who would object to doing this openly? Who would object of having all the other students, in principle, look at your demo? No one. Okay, so then we do it openly. So everyone then is invited to seeing how he is demonstrating the project to me. Okay, so everyone is invited to look at all the demos. They start at 7:40, and everyone now has to put down a time. Okay, I cannot do this in a fair way. I could roll dice, but this is just as fair as having this thing go around now. So I just let it go around. And those of you who want to demo next Tuesday, put a time down that is between 7:40 and 8:35 or so, right? Okay? And those of you who know that you will not demo next Tuesday, but most likely the following Thursday, do not put a time down yet, okay? You put the time down next Tuesday, all right? Those of you who intend to demo on Tuesday, put a time down now. Huh? Those of you who do not intend to demo on Tuesday, do not put a time down yet, okay? All right, so put the time down in front of your name. Okay, first column, just put a time and go in 5-minute increments. 7:40, 7:45, 7:50, any 5-minute slot that is between 7:40 and 8:40. Okay? All right. Last questions. Last questions about the first project. Shoot. Shoot.
As far as the interface goes, is it okay if there's like a big file, or do you want some sort of GUI?
The most primitive way that I would accept, okay, is everything is controlled by an input file. Okay, if you do not intend or do not want to spend any time on interface programming, console, line input, dials, sliders, buttons, fine with me. Okay, but somehow you have to demonstrate to me how you specify the parameters, the resolution, the file name, blah, 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 right, and all of that. So if that's an input file and you read it in, fine. That gives you minimal credit for the interface, say 5 points or 4 points. It only counts 5 points anyway, the interface. But if you go way overboard and you make a very slick and wonderful and easy to use interface, then you get some bonus points for that. Okay, but again, minimal interface, please. Focus on the mathematics and focus on producing pictures that look different for the tricubic and the trilinear. Okay, that's the most important thing, that you get an understanding of that. No? Okay. All right. So, what should I talk about tonight? Topics of tonight are two, namely vector fields. I want to talk about vector fields more, and I want to talk about. I want to begin to talk about the next topic, namely interpolation and approximation of scalar data sets. So, flow fields. Okay, motivation. I want to motivate topological visualization. Topology based flow visualization. Flow viz. Okay. First of all, there is a magic word in there, topology. Whenever there is a buzzword, a great word in there, you have to go to the library, you have to go to the web, and you have to grab 2 books and read them, right? Right away. That's what I do. So there is a great Dover book out there, I think, if I remember this correctly. Dover book, I think it's called A Combinatorial Approach to Topology, which is a great foundation to all this stuff. So there's a book, it's called, I believe, A Combinatorial Approach to Topology. The title is this title or very close to that. You will find it. And the Dover books are very cheap. They cost like $10. The question is always, how many books have you read today? How many newspapers have you read today? How many journal papers have you read today? Right? You are maturing international scientists. You always want to know what's going on in Asia, in Europe, in Africa, in the States. Read your newspapers. You want to know what the competition is doing. You have to read these transaction papers. Not all of them, but at least those that touch the area. And the other thing is when there's something very fundamental, where you really need the foundation, because you never took a course in it, you're a maturing scientist, you are supposed to be getting the books yourself and teach the stuff to yourself. So, I'm not kidding. There are certain things that is just not part of your required curriculum, but it's related to your research, the stuff that you love, that you want to grow in, that you want to make contributions to, then you have to read these journal papers, okay? Your major professor or your instructor in class, they will expect this from you. You have to do that. And the other thing is you have to get yourself at least some chapters from some basic books when you want to do some, research in an area that requires you to teach yourself some additional work. All right, so much for that. Motivation. Okay, how many streamlines are there in this room? The air is moving. There's a flow field here. How many streamlines are there? How many streamlines could I draw in principle? An infinite number, right? So how many do you draw? How many are enough? You don't know that. Where do you place the streamlines? Where do you let them start? I don't know. Okay? So therefore, take the most basic of examples, a 2-dimensional field around a disk-like obstacle. Okay, the flow lines will look like this, right? If the flow is coming from left to right, a constant flow initially, right? All these flow vectors are 1, 0 here. But once they hit this thing, then the wind is blowing, we'll have to go around it. So, well, when you compute streamlines, they will look like this, right? They will happily go around that. Forget about turbulence right now. So no eddies right now. This is slow moving flow. But then there will be two specific lines which will be of great importance, namely this line. Boom. Why is that line? Why might that line be important? There's another line which is important, namely this guy. Boom. Okay. Okay, and I'm saying these lines are probably very important to understand this flow. Again, I can draw infinitely many of these lines. But there is really just one segment or region. There's a segment 1, the upper part, and there's a segment 2, the lower part. Segment 2. And if there are two segments or two pieces, then there must be a boundary between them. Okay? So instead of worrying about how many seed points I have to place and how many lines are enough, I worry about just getting the boundaries between regions. That is the whole. That is one of the major reasons why topology-based methods help. Okay. All right. But how do you know that this is a particular streamline that's of importance? What is given to you? Well, what is given to you initially when you make this, it's just a bunch of points and vectors, right? This is the stuff that's given to you. All over you have a bunch of points with arrows at them. How do you know that only these particular lines are important? Well, what are the vectors on this line? What happens to the flow? Think about it intuitively. Okay, here are the particles, the air particles coming, and what will happen once they hit at this point? The flow will have to go to what velocity at this point? 0. Okay. Here, when they are hitting tangentially, somewhat the particles can still go around it, right? But certain particles, this is an idealized mathematical viewpoint, of course. When they hit perpendicularly to this disk-like object, then they cannot go around it. They are stuck. Okay, so that's why it's called a stagnation point or an attachment point. And this whole thing is symmetric. So on the other side, so this is a detachment point where flow is also 0 and then starts slowly moving and gets faster again and it moves away. Okay, so here it is very fast to begin with, and then it gets slower and slower and slower until it is 0. Okay, so this is called an attachment point. Attachment P and T, and this is called a detachment point. Okay, how can I use this? What is characteristic at this guy, at these locations? The flow is 0. The flow vector there is 0. There is no flow. Stagnation. Okay. Here also the flow is 0. At this location, the velocity vector v is a 0 vector. It's 0, 0. And also at an attachment point in a mathematically idealized world, this would be 0. Velocity. So how can I use this? Well, how do I use it? I first ask the question, in my entire field, do I have zeros? Do I have an attachment point, a detachment point, or many of those? And in this simplest of cases, I find 2 of them. Okay? Therefore, all I will do is I use these points, these zeros, as the seed points for streamline construction. Okay, so I will just have to walk here, backwards in time, it doesn't matter, to get this line, and I will march forward in time to get that line. And I'm done. I have an abstract view now. The abstract view is there's a circular obstacle in the middle, and there's a separator. It's called separating space that gives me R1, region 1, where stuff behaves like that, and the other one is region 2, where stuff behaves like that. Okay? And all the other curves in between, they are similarly behaved. I could draw infinitely many, but I don't care. I just want to know that there's a boundary between region 1 and region 2, And if you wanted to see a streamline in those, you could use one representative. Yes, you could draw one. That's enough, because all the other ones behave similarly in a qualitative sense, right? That's where this comes from. Now, of course, real-world flows or more complicated flows have many, many more critical points, right? Many, many more. So, but it's more complicated, right? More complicated example. More complicated example. More complicated example. Let me do the flow at very high speeds. Even this thing becomes much more complicated when you have high speeds. I already drew a picture of that, right? What happens then behind it? There's a vortex streak. So, more complicated example, and I use the example, a cross-section of an aircraft wing. Section of aircraft wing. Aircraft wing. And so, in our world of numerical simulation, everything lives in a grid or in a bounding box in some finite domain. So if this is a cross-sectional view onto an aircraft wing, this could be the wing. And now I just draw something where I know the result. That's why I can do it so quickly. Okay, so I give you the result. And here's the aircraft. This can be the flow. Actually, this is the lift under the wing tunnel. So what's going on there? I only have drawn the result of an analysis like this. And then I have to tell you how you get this structure. This is a topological structure or a portrait of the essence of the flow. There are no arrows anymore. There's only there's a relatively small number of the important lines. And these lines are called separating lines or boundary lines, or in Latin, separatrices. Okay? So this is separatrix. Separatrix extraction or computation. That is this whole topic. How do we get that? Again, there are the analogs of these guys, so-called attachment points and detachment points, where flow is hitting the aircraft wing and gets stuck, or where the flow begins to move slowly, leaving the aircraft wing. So these are those points. Here's a point. I assume that air is coming down, hits there, and gets stuck. Here is a point where things might leave and go in this direction. Then here, this might be a detachment point where air is leaving and moves like that. And this might be an attachment point. So it might be like this, and then air gets stuck there on the stagnation point. So these are critical points on the geometry. And so this is a so-called AT. Why? Air is coming onto the geometry and gets attached to it. That's why people call it an attachment point. This is an attachment point, another AT. There can be many, many, right? This is an AT. And the other ones are points where the flow is beginning with 0 and then it goes up. And these are called detachment points, DEs, DE. And so I give you the legend now. We need to find critical points. Okay, these guys are important. AT stands for where the critical points are points where V at a critical point P and T is the 0 vector, right? Detachment points, attachment points. DE is detachment point. P and T. And AT is an attachment point. All right, what else? There seems to be something else ongoing here, right? With this stuff. And there seems to be something ongoing here. And here's something ongoing, right? So these are critical points too. This is another type of critical point. Here's a critical point. This is the center of a tornado, right? Here's another center of a little tornado. Okay, and they have special names. This guy, where 4 lines come together, is a so-called saddle point. So this is an SP. SP is a saddle point. SP is a saddle point. PNT. SP. Okay, these guys are called foci or focal points. More specifically, sometimes stuff is going into the focus, and that is a so-called attractor or an attracting focus. Okay, stuff goes in, it's sucked into that tornado, and here sometimes stuff is leaving it, coming out of it. So that's a repelling focus. So this is therefore called an AF, an attracting focus, and this guy is called an RF, a repelling focus. AF, an attracting focus, attracting focus or attracting focal point, and the other one is an RF, a repelling focus. This is all there is to this particular flow. Okay, so this is the result of some kind of analysis. I gave you the result, and the question is, how do you get this result, right? What's the input, what's the method, and how do you create these things? What does this tell you? What does this picture tell you? This picture tells you everything about the structure of the flow. How many streamlines can I draw to show this picture? Infinitely many, right? I can make this infinitely dense and show a picture, a Gauss shaded thing, a lick-like figure all over, and my eye gets an idea. But the essential discrete structure is captured by this representation. Why is this interesting? Okay, so these are all coming in. That's the way I have to write. So these guys come in. If these guys come in, and these guys have to come out. Okay, here's coming out. All right. Here it's going in, leaving, hitting, leaving, and so forth. All right. So what does this picture tell me? It tells me that all the streamlines I could possibly draw in this region have qualitatively the same behavior. They are the same. Their geometry is different, but they all will look like that. Right? All of them. I can draw infinitely many, but here is a particular region that is left to this separating line. Okay? So this is a distinct region. Distinct region of flow. This region here, bounded by the domain and this curve. There's another distinct region, this region here, right? Where all the lines behave like this, more or less, have to behave like that. There's no other way for them to behave differently. Now you have to think about the other regions, okay? They are a little bit more harder to comprehend because things end in focus, right? Anyway, you will get an idea for that. Also then, there are some points that lie on the boundary of our little box that contains all the data. So these things also have to have names. They are well boundary points, and you put them into 2 categories. This is where the flow is incoming, so they are called incoming boundary points. And this is where a particular separating line, a separator, or separatrix is leaving, so it's an outgoing point. So this is a BI. This is the BI. This boundary incoming, and this is a BO, a boundary outgoing. Okay. So these are not critical points. There is a velocity there, whatever it is, and it's just when you start here, at some point you will hit the boundary and you say stop. So BI is a boundary incoming point. But these are not critical points, right? There is a velocity different from 0 there. And then we have a boundary outgoing. Boundary outgoing. All right.
Can you clarify? So all of those other points are critical points? The saddle points, the attracting...
Zero, no movement. Particles are coming in, get closer and closer, and have no way to leave that point. They get stuck there. Not in reality. Reality is different. This is a mathematical...
Right, but like, what about the repelling focal point? I mean, that's a critical point, too?
It's a critical point. These are critical points. The detachment points, the focus, both types of foci are critical points. And this guy, the saddle point, is also a critical point.
Okay, and then the saddle point, does that happen anytime the flows cross, or it's only a saddle point if the flows cross and the flow is kind of, as we see, equal and opposite coming out?
All right. These are the next things I have to talk about, okay? Again, this is a very simple type of topology that depends on the underlying polynomial behavior of the definition of the field. This is based on linear vector field theory. These types of depictions are only valid for linear vector field theory. Okay, I'll come to that. So, these are all critical points. Detachment, attachment, saddle points, attracting foci, repelling foci. These are all critical points, okay? All of these guys are. These are all critical points. These guys are not critical points. All right, so what do you have to read? There is a paper. You have to read this one paper, or many papers. Papers by Lambertus, Hesselink, he's Dutch. And the other issue is this type of a picture is only valid for, this is based on linear vector field theory. So linear vector field theory. So there's a lot of research to be done, and I would like for some of you guys to consider doing Project 4 based on this. Project 4. So this is all done, but what comes next could stimulate you about your, right, could provide stimulation for the last project. How do you get this picture? How do you get the picture? First step is you find the critical points, all of them. You ask, where do I have the flow field being 0? The answer of the analysis will tell you it's 0 there, it's 0 there, 0 there, and then it's 0 at these 4 points on the geometry boundary. That's it. Okay, that's the first intermediate result, but you want the curves. Okay, what next do you have to do? From all of these critical points on the geometry, the boundary, you start streamlines. You seed. Okay, you use in a little finite neighborhood here. You have to have a seed point, but the seed point has to be just perfectly chosen. So when you compute the streamline, you get exactly that thing. You go backwards in time, but it doesn't matter. You want to get that geometry of that boundary. Okay, so from all these points on the wing, you start streamlines. Okay, you get one here, you get one here, and you get one here. All right, and then you have these other critical points, these foci. You do not start anything there, but you start things at the saddle point. How many streamlines do you have to start at a saddle point in a little neighborhood around it? 4. You have to go in 4 directions. You see that? A saddle point will be the seed point for 4 streamlines. Namely, you start here, a seed point here, a seed point there, a seed point there, and a seed point there. And then you ultimately will get this guy, you will get this guy, you will get this guy hitting the boundary, and you will get this guy. You have to stop. It's another thing. When you run into these cycles, you have to figure out that you're in a cycle and stop. So you have to stop when you are, have a winding number there, going around at least one stop, or when you hit the boundary stop. You have an idea how this works? You want this picture. How do you get the picture? You first find all these zeros, these critical points, and then you identify those that lie in the geometry, and you find these SPs, or saddle points, and from those points you let these streamlines go, And where will they go? They will go to other critical points, or they will hit the boundary, or they might hit the geometry again. Okay? From geometry point to geometry point is possible too. All right. Do you believe that this is important? This is good? This is a much simplified, a very simplified view of a very complicated field? Yes, it is. Okay. So far, so good. Now, linear vector field theory. Should I hit on that? Why that is important? Yeah. In linear vector field theory, the only types of saddles you can get is this type of saddle. Don't copy this. Okay, this only goes to your question. So, linear vector field theory, the only type of saddle behavior one can get is this. There's a saddle point, and it has 4 happy quadrants lying around it. And it's always this dual behavior. 2 lines have to come in, and 2 lines have to go out. The way I've depicted it here, it's going out, it's going out, it's going in, it's going in, and so on. That's it. But if I can do something with 4 regions, then I also can do something with more regions. More regions as in 6, for example, right? This is a saddle point 2. And I always said there's this alternating behavior, because going in, going out, going in, going out. You can do this with an even number of these lines, right? Say going in, going out, going in, going out, going in, going out. So what is the portrait of this thing? Well, here the flow looks like that. Here it looks like that. Here it has to look like that. Here it looks like this. Here it is this. And here it looks like that. That's combinatorially the only stuff that can happen for 6 regions. Okay? There's nothing with 5. Okay, it's even numbers of regions. But this type of this is a so-called higher degree, a higher degree saddle. You can never get that when you are stuck with linear vector field theory. Okay, so most of the papers and most of these topological analysis out there are done based on this assumption that everything is linear. Obviously, nature is much more complicated. Nature doesn't know about the linear element, right? Nature is nature. So, in order to capture this, you need to use different polynomial schemes. If I can do it for 4 and for 6, I can do it for 8, 10, much more complicated stuff, right? All right. Anyway, this is research. If you want to do that, then you can think about, well, is there something like a quadratic vector field theory, higher degree, higher order vector field theory? There's some initial work done in that area, but not a lot. Okay, so this is cool stuff.
So what is
territory for research? Yes, shoot.
What exactly is the definition for that makes it linear vector?
Oh, let's see example now. We do a very simple example. What's the linear polynomial? F of x equals a linear polynomial in one variable called x is of the form f of x equals a times x plus b. That's it. So linear vector field theory is only about that. But for 2D or for 3D. And this paper is about how you can compute these curves exactly without error, without numerical error. I talked about error, right, last time. There is a way to compute these guys without error, analytically correct as complex exponentials, when you go to solutions of systems of ordinary differential equations. Anyway, so an example. We do an example. An example will help, right? Examples should help. I fully realize that I'm starting doing this backward, right? In this case, I give you this this interesting picture which looks like art, and I tell you it's meaningful, right? But what's the building block? How do I get this picture? So this is what I assume. So if this is your data set, don't copy this. This is just motivation. If you have a data set that is a triangle mesh, you have a bunch of triangles. In computation, people use these meshes or grids, right? So assume this is a very trivial form of a triangle mesh. And what you have are the vertices, and maybe you have happy vectors there, okay? That's your input. You have this triangle mesh with all these happy vectors. And now you want to do an analysis on that data set. An analysis that gives you some kind of depiction, maybe that looks like that, right? So where is this curve? So the basic building block is the triangle. The points, the corners of the triangle with the vectors there. And then you need to be able to do an analysis for a linear element, for one triangle. If you understand how the analysis works for just one triangle, then you can do it for the entire mesh, and you can make pictures like those. Okay? So we do a simple example, and I even show you how you build the linear polynomial to begin with. Okay, a simple example is a happy so-called standard triangle. If this is my x direction and this is my y direction, then these are my vertices, and I want to make it simple, so this is location 0, this is location 1. Here is another happy vertex, here is another happy vertex, and this would be 1, this is 0. I have to give these guys names. I call this point 0, I call this, no, better misindexing, starting at 1 this time. So this is point 1, point 2, point 3. And I have vectors there. So again, let's make it simple. Let's use this vector here. Let's use this vector here. And let's use this vector here. Okay. This thing, this configuration, already implies a particular type of behavior. If you're experienced, so if you are very intuitive, you already know what's going on there qualitatively. Do you see it? In order to analyze this in a topological way, the first thing you have to do is you find a critical point. Is there a critical point here? Where is this? What type of a critical point is it, if there is one? And once I have that, which are the directions in which I have to start my streamlines to get these separators, right? These separating curves. Okay? But this is the input, the simplest input, that is the only allowable input if you want to stay in the space of linear vector field theory, because only linear polynomials are allowed. Okay, where are these linear polynomials? We build it. So this vector would be -1, 1. This vector here should be 1, 1. And this vector should be -1, -1. Okay? I should draw them more longer, but I don't have the space. Okay, so now I build the vector field. The vector field for this would be u, v, are functions of x and y. And so if they are linear functions, they will look like this. They are functions that look like a times x plus b times y plus a constant, right? It's a linear function. A times x plus b times y is linear, not more than that. And down here, maybe call it a bar times x plus b bar times y plus some c bar, okay, for the second component of the vector field. Okay, how do I get the coefficients a, b, and c? I have 3 points, and there are 3 associate vectors. That gives a linear system of equations. I can solve for the coefficients, right? So now you have a linear system of equations, EQs, and you remember this Gaussian scheme, how you write that down, right? You plug the different locations in there. If this is location 0, 0, and this here is location 1, 0, and this location here is location 0, 1, you just plug these coordinates, x, y, into that equation, and on the left-hand side you have the uv, the associated vector. And the unknowns are the a, b's, and c's, and a bars, b bars, c bars. So you can write this as a or a bar, b, b bar, c or c bar, and on the right-hand side you have the values, the u's and v's. Okay. Now I might do this quickly, but I just plug 0, 0 in there, and on the right-hand side I want to get -1, 1. Okay. I plug that into the equation, and what do I get? I get 0, 0, 1 equals the uv guy. The uv guy is -1, 1. Okay, now I plug the second point in there, this guy. So x and y become y and 0, respectively. And on the left side, the vector is 1, 1. So x is 1, so that means 1, 0, 1 should be the vector there. The vector is 1, 1. Now the last point is this guy. So this point is 0, 1. So for x and y, I plug in 0 and 1. And the vector to come out is -1, -1. So it's no x, 1, y plus c plus constant should be going down to the left, -1, -1. So that is setting up the linear system. Now I do Gaussian elimination, right, blah, 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 subtract the equations, this guy minus that, and this guy minus that, this becomes third equation, then I have the solution on the right. Remember that, so I do Second equation minus, you guys can remember that. I can number this, right? 1, 2, 3. So the first one I want to do 2 minus 1, and I get 1, 0, 0, 2 minus 1. 1 minus minus 1 gives 2. 1 minus 1 gives 0. Next equation I want to use 3 minus 1. 3 minus 1. 0, 1. It's okay, that gives me 0, 1, 0. This guy minus that. Minus 1 minus minus 1 gives 0. Minus 1 minus 1 gives minus 2. And then the first equation I can copy, right? It's just the first equation. It's 0, 0, 1 is minus 1, 1. And this is the solution. So that was just Gaussian elimination. And now I can write down the definition. Okay, so what does this mean? The solution says, well, now I plug these coefficients back into my expression there. It says u and v are some matrix times x and y plus the constant vector, right? And the matrix is 2, 0, 0, minus 2. 2, 0, 0, minus 2. And the vector to be added is minus 1, 1. Minus 1, 1. That's the solution. U of xy is 2 times x minus 1. And v of x and y is minus 2y plus 1. That's my definition of that linear vector field. Okay. All right. Now we have to follow our intuition. We always want to follow our intuition, right? As scientists. Do you see the portrait here? Do you see the structure already? Is there a critical point here? Where could it be 0? Where could the vector be 0? You see it? This one is going this way. This one goes the opposite way. Could they annihilate each other and make each other 0? At the midpoint, maybe. If I do linear interpolation along the edge, that's what it is, right? I do linear over the triangle, that means I do linear over the edge. This goes this way, this goes this way, opposite way, so half point they should be 0. So there must be, this is just intuition, okay? We have to verify that. But my intuition tells me that there's probably a critical point here. My intuition further tells me that the flow here looks like this. Okay? This critical point is a saddle point. Huh? This one here is like that. But inside the triangle, it looks like this. You need to have this intuition. Is this intuition correct? Well, we have to find the critical point. Where is it 0? We have to set this guy to 0. That is always step number 1. Find critical point. Find critical point. That means we have to set this to 0. So you say 2, 0. You don't have to copy all of this. I know that you can do that. X, y plus 1 minus 1, 1 equals 0, 0. Okay, now you solve this for x, y. You have 2 times x equals 1. Right? 2 times x equals 1, so x equals 1/2. And then you have minus 2 times y equals minus 1, so you also have y equals 1/2. So you get 1/2, 1/2, 1/2. Right? See that? Okay, so you solve that, and I know you can do that, so you get x, y out of this. And the critical point is 1/2, 1/2. So our intuition was right. There is a happy critical point living on the edge of the triangle. Okay. Second, and now I just give you the recipe. You have to read this paper by this Hesselink guy, Bert Hesselink. He's a professor at Stanford in mechanical engineering. So, what type of a critical point is this? My eye tells me this is a saddle point. This was intuition, right? An experience. But there must be a classification when a critical point is a saddle point, when it is a focus, and when it is something else, right? And I just put this over there. There is a classification of critical points. And so you will see the classification in this Hesselink paper. If one needs this Hesselink paper, this theory is hundreds of years old. It comes actually out of dynamical systems, right? So, for example, you have a pendulum swinging, and it will go like this, right? Happily go around, and will be going around the focus. Then you have the planets going around the sun, so the sun is at the focus as well, things like that. It comes out of dynamical system theory. Hesselink paper tells you about the classification of critical points. Classification of critical points, of critical PNTS, critical points. What critical points are there? There is first a saddle. I just call it saddle. Okay, it's a saddle point. A saddle always looks like this. The critical point is there, and there are 4 distinct streamlines coming together at it. There's another one called a center. What is a center? Stuff just goes around it forever. Orbits. So there is something called a center. And a center critical point looks like this. How do I depict it? Nothing is ending at it, but all the streamlines in its neighborhood are concentric circles going around it, right? You can think of it as the orbits of planets going on a circular or elliptic trajectories. And the other guys are foci. Foci, so they look like this. Again, in linear vector field theory, these are the only ones that can happen. And then you have the orientation thing. These center things can go clockwise or counterclockwise. And then the spirals either can be sucking or spitting things out, right? So again, this can go in or it can come out. And here again, also the orientation for centers, they can go in this way or they can go in that way. All right. Here's a saddle, right? And so, and this classification is based on an eigenvalue analysis of this matrix. This matrix is called the Jacobian of the flow, or the linear vector field. And you have to look at the eigenvalues to determine whether you have this case, and that case. And you're in a finite world again, because you only have to look at the signs of the eigenvalues. So the eigenvalues of the Jacobian determine the type, determine type of critical point of critical PNT. All right. So we have to determine the type. So this guy is a critical point, right? A critical point, but we don't know what type it is at this point. Critical point. But what type? Determine type of the critical point. Critical point. And so this is our equation, our linear equation system defining the flow. And we have to look at the Jacobian, or the Jacobi matrix, Jacobian of star, which is a part of the matrix given by the partial derivatives of the expression with respect to x, with respect to y. In the linear vector field theory, the Jacobian happens to be this matrix here, okay? So the Jacobian J, in this case, is 2, 0, 0, minus 2. Okay? As I said, you have to look at the eigenvalues of the sky, of what sign they are, to determine what type of a critical point you have. So we have to do the eigenvalue analysis. Oops. So eigenvalues. So we have the characteristic polynomial, right? The characteristic polynomial of that thing, lambda. This is determinant 2 minus lambda, 0, 0 minus 2 minus lambda. You remember that. That's the determinant. Blah, blah, blah. Wait, this is polynomial 2 minus lambda times minus 2 minus lambda. And then you have to set this thing to 0 to get the eigenvalues. And so char of lambda, characteristic polynomial, has to be 0. And so if this expression has to be 0, then you get the first eigenvalue lambda 1 to be, well, 2 minus 2, right? 2 is 0, and for the lambda 2, when is this guy 0? Minus 2 plus 2, so it's minus 2, right? Lambda 2 is minus 2. Okay, those are the two eigenvalues. And now you go to the Hesselink paper, and this is a particular type. You have two real eigenvalues that have different sign, and that is the case when you are dealing with a saddle point. Boom. So case lambda 1, lambda 2 are real and have different sign. Are real and have different sign. Have different sign. And therefore, we are dealing with a saddle point, or with a saddle. I just say saddle, okay? We have a saddle. Okay, this is all good. What does this tell us? This tells us, from a saddle point, how many streamlines do I have to start as a saddle point? 4. Therefore, I also need to know the directions in which I have to go, because I cannot start my streamlines by having a seed point at exactly the location of the saddle. Why? I would always stay there. The saddle point is where the flow is 0. It is not a valid seed, right? My numeric integration scheme would never be able to leave it. I get stuck. So therefore, you need to know what the eigen directions are, and then you can go a little bit off in these eigen directions to trace out these 4 streamlines. Okay, again, I give you just this example with the essential steps. So we also need the eigen directions to know in which directions to trace. Need to know, and this is part 3. Need to know eigen directions or eigenvectors. Eigenvectors of the Jacobian at this critical point, at 1/2, to be able to trace 4 streamlines, to trace or to compute 4 streamlines. Okay, so now I need to do an eigenvalue computation. Now for lambda 1, I can do that. What is this eigen vector computation? You say, well, the matrix, we are only concerned with the Jacobian, 2, 0, 0 minus 2 times, now I want the eigen direction, I call that maybe direction dx dy, should be the first eigenvalue, which was 2 times the direction, should be 2 dx, 2 dy. Okay, and so now you get an eigenvector from that, right? So what do you have? You have 2 dx equals 2 dx, so dx is anything, and you have minus 2 dy equals 2 dy, which is true only for dy being 0. So you get 2 dx equals 2 dx, that's the first equation. Second equation says minus 2 dy equals 2 dy. Okay, from that, you see that dx is free and dy has to be 0. So you get the first eigendirection, I just call it eigenvector E1. I can choose it 1, 0. It's nice, right? For lambda 2, I compute the associated eigenvector by again doing the same setup of equations, 2, 0, 0 minus 2 times the unknown direction, eigendirection, dx dy equals, in this case, eigenvector 2. The eigenvector 2 was minus 2 times dx and minus 2 times dy. So from this I get the equations 2 times dx equals minus 2 times dx, and I get minus 2 times dy equals minus 2 times dy. So I get 2 dx equals minus 2 dx, and I get minus 2 dy equals minus 2 dy. So in this case, dy is free, and dx has to be 0 for it to be true. So from here, I get my second eigenvector, d2, which I can choose to be 0, 1. Okay. Now I can use this usage for this particular example. I have my happy triangle. I had my points, my corner points. I had my vectors here. Now I know I have a critical point there, this guy. I know that this is a critical point of type saddle, and I know there are two eigen directions. The first one is given by this vector, eigen direction 1, 0, and the other one is going in the direction upwards, 0, 1. Therefore, I have to trace two curves in the positive direction of these vectors, and I have to trace two curves in the negative direction of these vectors to get all four. So therefore, this was eigenvector 1, I guess. This was eigenvector 2. This is my happy critical point, my CP, which is a saddle. Right? And so I also trace lines in the opposite directions. Okay. How do I trace? Well, as I said, I cannot use the critical point itself as a seed point. I have to move off it by an infinitesimally small amount, right? In which direction? Well, in direction 1, 0, 0, 1, minus 1, 0, 0, minus 1. And then you have 4 seed points, right? The 4 seed points would be here. And from there you construct your separators. And then you would get this guy, you would get this guy, you would get that guy, and you would get that guy. And you get 4 separating lines. You get 4 separators, 4 or separatrices. And the flow, now you can depict the flow, right? This is what the flow looks like, has to look like. This is what it has to be here. This is what the flow here. And of course, you also know what it's there outside the triangle, actually, but you know, it has to be like that there. But inside this triangle, you have 3 distinct regions. 3. That's it, right? Region 1, region 2, region 3. And you know, in this particular region, everything behaves like this. Right? In this region, everything behaves like this, qualitatively. Right? In this region, everything behaves like this. Right? And you only have to really draw one representative curve in there, this guy, and that guy, to characterize the entire flow. Right? To get more abstract views, abstract depictions, that's why you need this stuff, use this stuff. Did the example make sense? All right. This paper here is a paper of great importance. It allows you to compute these curves without using a numerical scheme. Okay, it gives you the exact analytical formulas for these curves. For certain things, namely for these things, for linear triangles, these arcs do not have to be computed numerically with xi plus 1, xi plus 2, right? You can only do errors by doing that. I talked about it last time, right? These numerical recipes, how to do that. In this case, linear vector field theory, all these curves have an analytical form, and you can use the analytical form to compute a bunch of points that lie exactly on those curves. And that's spelled out in the paper. So, remark 4 a linear vector field streamlines are the exact solutions of, what is this called? This is a first order inhomogeneous system of differential equations, right? Of first order inhomogeneous systems of differential equations with constant coefficients. Differential equations with constant coefficients. Okay. So these are the buzzwords. Buzzwords are, there's a differential equation somewhere, and there are many of them. So there's a system of differential equations, and then they're of first order, and they're inhomogeneous because on the right-hand side I have something that's different from 0. Constant coefficients means that the factors or coefficients in front of the other variables are constant numbers and not functions in their own right. Anyway, look up your textbooks. And when you go to the textbooks for these class of systems of differential equations, you can solve it exactly, which is very nice. So, so these things, u, v of xy equals some matrix a11, a12, a21, a22 times xy plus some constant 1 and constant 2. This is one of those particular types of equations that for which the solution for the stream curves is exact. You can also write this down in an equivalent way. And I know I'm doing this fast. Equivalent way is uv are the components of the velocity, but velocity is nothing but the change of location over time. So they are sometimes called x dot and y dot. So this is another way to write this is x dot of t, and y dot of t is this matrix M, right? There's a matrix M. It's M times this x of t, y of t, plus some constant, plus a constant vector c. Okay. So you have the velocity of particles defined in their position. You want to solve for x and y. That's the that's the differential equation context. For this, you can solve it exactly, and the depictions, illustrations of the exact solutions of typical exact solutions which are of a certain type, which are of type, now they are parametric curves, x of t, y of t equals, and usually they look like there's some kind of constant alpha times the eigenvector 1 times the exponential e to the first eigenvector lambda times t plus some constant beta times eigenvector 2 times exponential of second eigenvalue lambda times t plus some vector constant. This is a general solution of that thing. and again it's in the textbooks. These are the eigenvectors that we just computed. These are the eigenvalues of the thing that we just computed in a very trivial example, which are of type blah blah blah. Look as follows. And it's amazing that you indeed can intuitively grasp the meaning of that. Does this represent, can a triangle and a linear element depict something that is of center type? It should, according to linear vector field theory. And should I be able to represent all the orbits exactly in an analytical form? Yes, it should, because there's this thing, right, from solving differential equations. Can it represent saddle points and then these foci? Oh, let's see. If I have a triangle like this, a triangle, 3 points and 3 vectors always imply one unique linear polynomial, right? And this thing, this representation of the flow field, is a system of these types of differential equations for which you have an exact solution. If I give you this vector field behavior, and now follow your intuition, your gut feeling tells you what is that? What is the behavior there? It's the center. Someone said, who said it? $5. $5. Obviously, right? Has to be this, right? You see that? Okay. So there's a critical point there. The critical point is, of course, the sun. The center, right? Then you do an analysis of what type of critical point it is, and this Hesseling paper and its lookup table, based on the eigenvalue analysis, will tell you this critical point is the center. Now, you want to draw a bunch of streamlines for this. And the Nielsen paper tells you that you can get them exactly. They are of this form. This is an initial value problem, so you would specify an initial value on any of these curves, and you would get exact circles. With a numerical scheme, you would never be able to stay on an exact circle. You would always miss the starting point. This is very important to get this. If your orbits are orbits, you better want to make sure that the Earth will continually revolve around the sun and won't fall into it. That's a slight distinction between the center and the focus. You see that? When you're off a circular or elliptic orbit, you will fall into the sun or will drift off to nirvana. So, okay, very important. If something is a center, all the streamlines in its neighborhood have to be closed orbits. Okay? You want to, if this is my seed point, then what should I get as a streamline? An exact circle or ellipse, okay? Boom, coming back to the exact start point. If I use any of these numerical schemes that I talked about before, you will never get that. You will always get something like this. That's a mismatch, right? No matter how small your epsilon is always greater than 0. It can never be 0, right? Because then you would need infinite sampling. All right, so you believe me that this might be good. So I can also start here, right? This linear polynomial is defined everywhere, not just inside the triangle, but everywhere in the entire xy plane. So I can have any arbitrary number of seed points, and I get circles everywhere. Right? That's what I get with this method spelled out by Nielsen. Okay, the other case is, well, the case that we just had, right? This type of a triangle. This. And yes, here's a critical point. You got that. And now again, you want to have a bunch of arcs rendered in this triangle which are exact without numerical problem. And the seed points, for example, could lie here on this boundary, because you want to know where the streamlines enter and where they exit. That's what you want. And you would get these exact arcs, and for each of these arcs, you would have the seed locations lying on the boundary edge, and then you would have a definition of these guys in analytical form, and you find out where they exit, where they hit the boundary of the triangle again. But in the meantime, these guys are complex exponential functions. They have to be able to represent the circular behavior too, and you remember that complex exponential functions, cosine ix equals cosine x plus I sine x, right, by Euler's equation. So circular behavior can be encoded by the complex conjugate solutions of these equations as well. Again, this is the textbooks, right? So the other thing is, of course, you can get this behavior also. Okay, you can get these. Relevance. Why is this relevant? The relevance is the example that I gave you, a topological analysis around an aircraft wing. Okay. What is given to us? Not this particular portrait that I had on the board before, but a triangle mesh. A triangle mesh with a bunch of vertices or corner points plus vectors or arrows at those corner points. This is what is given to you. There's a bunch of triangles living here. You get the idea, right? All right. And when we find our zeros, in the case of a triangle mesh, and we want to find whether there are any detachment or attachment points on the geometry of the aircraft wing, or the aircraft wing itself, the way it's given here is just a polyline, a closed polyline, right? We have to find zeros on these edges. Are there any? Well, yes, there is this one right there. Okay, there is one. There is a critical point. It is not a critical point, but it's a critical point where the velocity is 0. And now I would like to have a streamline starting at this point. That's what we said we were going to do, right? We take all the AT points and the DE points, and we want to compute good separators, ideally without error. All these methods I talked about last time give you error, and sooner or later you deviate from the exact streamline. But with this Nielsen method, you stay on it exactly in each triangle, right? So there is one of these separating lines, which is now piecewise exact, well, exact in each triangle. This will be the seed point. There will be, this is the entry point to this arc. There's the exit point, right? This particular arc is exact. There's a function for that, and the function looks like this. Now, this guy is entering the next triangle. You get a new arc, exactly. Enter point, exit point, entrance, exit. A new entrance point, a new exit point. Exit point becomes entrance point here. Bam. The whole thing will consist of exponential functions, which are the best possible separating line that you can get for a triangle mesh. There's nothing that you can get that's better. It's in the spirit of linear vector field theory, and it's exact. Each of these little arcs or curves is analytically defined as a function. Not as a polyline sequence, but for rendering purposes, then you can evaluate x of t and y of t, and you can draw 1,000,000 points on this line, okay, for high quality rendering. I hope I got this across why this is related, okay? Linear vector fields are very complicated. Linear vector fields are relevant in the context of dealing with triangle meshes. Triangle meshes imply a linear polynomial description for x and y, for u of x and y, v of x and y. They allow me to actually construct any streamline inside the triangle exactly in an analytical form, and therefore I can use this recipe to compute these so important separatrix lines in a way where there is zero error. Zero error. That is really very powerful. Okay, makes a big difference whether you have to compute a line that looks like this with a numerical scheme where you have this happen, right, and you drift away from it more and more, right, or you always stay on it no matter what, right, because you have an exact analytical definition. If the streamline is a circle, then what comes out here? If you have a circular streamline behavior, and it's a circle, then you get x of t and y of t being the definition of the circle. It will give you a cosine of t and a sine of t. Boom. And you can evaluate this parametric definition of the circle with as many points as you want, and you always stay on it. Okay? So you get these types of functions out of this general solution. There are two equations here. One for x, one for y, because these guys are vectors, right? The first and the second component for x and y. These are really two lines. So again, I strongly encourage you to read up on this if you're interested in this. This is in your textbooks on differential equations. You remember it, right? You definitely remember it. So differential equations, and then there's different categories of differential equations, right? Different classes. And this particular class you have to read up on. First order systems, inhomogeneous types of systems with constant coefficients. And then there's a Wronski determinant, and you have to get the general solution for the homogeneous system. Then you have to get one special solution for the inhomogeneous system. Then you have the initial condition, right? The condition for where the thing should start for the time point 0, and then you get the closed form solution, okay? Many, many pages of derivation, but it's in the textbooks. Right? Do you remember that vaguely? If not, I don't remember it. What do I do instead? I use Mathematica. Mathematica is powerful enough, right? In Mathematica, you just feed the little equation. Mathematica, you just feed this thing. UV equals the matrix times xy plus a vector. And Mathematica will give you this back. Boom, what the closed form solution is for that thing. It does this all for you with computing Wronski determinants, general solution, inhomogeneous solution, combining them, initial value. For in Mathematica, you would just give this matrix, right, times xy, plus this vector there, blah, blah, blah. In sum, you would give an initial condition, x0, y0, the initial location. Huh? So Mathematica would give you back cosine t, y of t, and you say, initial condition, boom, and this comes out. Mathematica, linear algebra package, whatever you like, MATLAB. Okay, just want to motivate a little bit the next topic, what it's all about, and then I will finish. Is this good enough for 3D, what I talked about tonight? Gee, it was not even good enough for 2D, right? Even for 2D, it was only good enough for linear vector field theory. There are linear vector fields, there are quadratic vector fields, there are cubic vector fields, there are real world vector fields, which are completely different. These are all mathematical idealizations that don't exist, except in our head. So, yes, there are higher degrees, and then in 3D, all of this generalizes and gets really complicated in 3D. What are the critical points in 3D? Is there any critical point in this flow around us where particles are coming together and boop, stagnate, get stuck, and there's no movement at all? Maybe there are a few. Maybe in some corners, or here there are some stagnation points. Okay, you see that when the leaves are falling, and you go to your balcony, and you see all the leaves have happily accumulated in one particular spot. That spot obviously is a spot where the leaves were able to get to, but were never able to get out of. Right, so a stagnation point. You see that? Parking lot, right? There's these piles of leaves. They are just lying there, concentrated on my bicep, because that's where the velocity is. So there's a visualization of them, but the flow is really 3D. So what are the analogs of critical points in 3D? Critical lines, okay? And they're even much more complicated to characterize. All right. Next topic, scattered data approximation. And again, this can be used for project number 4, if you like this stuff, okay? There's so much unconquered territory in this area of topological characterization and visualization of flows and other things. It's endless, okay? You can easily grab complicated research problems and worthy ones. Scattered data approximation. Just illustration, defining the problem tonight, and then I will stop. So scattered data means, typically this is how that originated. We have a bunch of locations in the plane. The locations or sites are my happy circles here. At these sides, we have function values, which are these sticks coming out, going up. All right, and the values are the bullets. And so what is given is a set of tuples, locations xi, yi, and the dependent measurement of function value fi, and you have n of them, I from 1 to n. Okay. So this guy is location xi, yi, and it has function value of fi. What do we want from that? We would like to be able to actually have a surface constructed on top of all these sticks, right, which are kind of just like alluding to this tent, but we actually have to construct the tent surface on top of those sticks. That's what we do. So we want to have a function, right, that when depicted were to look like this. Okay, so function above it, and you get the idea. So we want something, wanted. We want a function that we can evaluate everywhere. A function fctf that satisfies a condition when I evaluate the function f at a given site, then it reproduces those values there, my initial measurements, right? I want a function that I can evaluate everywhere, but it must reproduce the given function values at the sites, of course. So this would be a site. Okay. How do you do that? I have 1,000 temperature measurements in this room, but I would like to estimate or approximate the temperature in any location in this room. So therefore, if I'm standing here and I have a few temperature readings in my close neighborhood, then what's the temperature at my thumb location? Probably some average of these temperatures at locations where I have readings for, right? So that's the whole idea. If I have a bunch of readings, temperature measurements in this room, then I blend these together, I mix them up in a good way so that I can approximate or estimate temperature values everywhere in this room, right? That's the whole thing. So and the other underlying fundamental is, if I have readings that are close to my body, then those readings are more important to having estimates, right, in this area than the readings far in the corner. The data close to me as a point should have higher influence on the estimated value where I am than the stuff that's far away from me, right? Okay, so we have readings, and we have to mix them together in such a way that the stuff far away from me has low weight or low influence, and the stuff close to me has high weight or high influence when I approximate or estimate a value here. Right? That's the whole paradigm. And the trick is to come up with a good way to combine or to blend or to weight the different readings together. Okay? That's the whole trick. All right. Thank you so much. Kate, shoot.
I forgot to remind you that there was maybe another volume viz data site.
Uh-huh.
So
Right.
now I'm reminding you.
Great. Please tell me, where is it?
You never told me where it was.
Oh, please find it. Please find a good one besides the volvis.org, and the next time we put it on the board. I should have told. Sign up.